Welcome to The Explainer. I am your host, your lead strategist for all things math, and today we are tackling a topic that literally strikes fear into the hearts of candidates across the globe. I'm talking about Cambridge IGCSE Additional Mathematics, Syllabus Code 0606, and the dreaded cubic polynomial modulus graphs, specifically sketching them when they are given as a product of three linear factors. Right now, I want you to picture a real past paper question. Imagine it's from the 0580 or 0606 series. You're sitting in the exam hall, the clock is ticking down, you can almost hear it, and you see it. Sketch the graph of y equals the modulus of x minus 1 times x plus 2 times x minus 3. Your heart races, your palms sweat. Now I want to introduce you to two archetypal students we see in literally every single exam session. First, there's Alex. Alex overloads his answer with raw mathematical facts. He calculates a dozen individual coordinates, plotting them meticulously one by one, but he shows absolutely no analysis of the curve's fundamental shape. He wastes 10 whole minutes on a 3-mark question. Then there's Sam. Sam rushes. Sam completely misses the specific command word sketch and tries to draw the whole thing to perfect scale, completely missing the critical features of the moduli. If we were looking at their papers side by side right now, you'd see a sea of red pen marks. We are going to look at their flawed approaches and exactly how you can avoid their fate.
Look at this insight on the screen from a senior Cambridge examiner. Let that sink in for a second. The difference between a B and an A star comes down to how well you understand cubic polynomials and their moduli. We are absolutely raising the stakes today because we are about to decode exactly what examiners are looking for. They aren't just looking to see if you can blindly plug numbers into a calculator. No, they are looking for a master chef. Think of your exam strategy as a recipe for success. You need your evidence, which are your raw mathematical ingredients. You need your analysis, which is your actual cooking process. And finally, your evaluation, which is your beautiful, flawless plating. When you encounter advanced syllabus codes like 0606, or even moving up to the incredibly demanding 4024, 4037, and 4040 series, the examiners are actively separating the students who just memorize from the students who truly understand the recipe. And by the end of this explainer, you are going to become the latter.
Okay, let's dive into this. Here is our roadmap to systematically eliminate that exam anxiety once and for all. First up, the A-star difference, the complete mindset shift you need to make. Second, the core conceptual principles so you can hit those strict academic benchmarks. Third, the standardized sequence for your technical methodology. And finally, top examiner warnings, where we're going to uncover the most common traps that students fall into year after year. Let's start with our first agenda item, the A-star difference. Making the leap from a good grade to an elite grade requires a fundamental shift in how you view mathematical problems. You have to stop looking at a cubic equation as a chore and start looking at it as a story waiting to be decoded. And to decode it, top students use something we call the PL framework, adapted specifically for mathematics. Point, evidence, explanation, and link. You make a mathematical point. You back it up with evidence, like a calculation. You provide an explanation of the graph's behavior, and you link it back to the specific command word in the question.
This brings us to a massive concept. The assessment framework heavily prioritizes analytical depth over superficial breadth. Superficial breadth is what Alex was doing, calculating 20 different coordinates without understanding the curve's actual behavior. It's a waste of time. Analytical depth, however, means completely decoding the mathematical command words. When Cambridge says sketch, they absolutely do not mean plot. They mean show the key features, the intercepts, the general shape, and the sharp cusps created by the modulus reflection. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, back to the strategy. Top students structure their answers methodically using that Peel framework. Their point is identifying the roots. Their evidence is the zero values of the linear factors. Their explanation is the underlying cubic shape. And their link is applying the modulus effect to reflect those negative values perfectly. Moving right along to our second section, core conceptual principles. To hit those top-tier Cambridge academic benchmarks, especially in the 4037 and 4040 papers, we need to build a rock-solid theoretical foundation. Think of this as getting your ingredients perfectly prepped before you even turn on the stove. If your foundation is weak, the intense pressure of the exam hall will cause your entire strategy to just collapse in on itself.
The theoretical architecture of this topic really rests on these three pillars. First, precise definitions. What exactly is a modulus? You know this. It's the absolute value, the non-negative magnitude. Second, causal relationships. You need to intimately understand how a linear factor, let's say x minus 2, directly causes an x-intercept at positive 2. one causes the other. And third, cross-topic connections. Guys, this is where the magic happens. Principal examiner reports continually highlight that candidates who reference cross-topic connections, like linking graphical solutions to algebraic inequalities or seamlessly connecting functions to coordinate geometry, achieve significantly higher marks. If you can show the examiner you understand how a cubic modulus graph relates to finding the domain and range of a function, you are practically guaranteeing yourself a top grade.
So the crucial takeaway here is systematic analysis and evidence-based reasoning. This is your cooking process, and it is completely non-negotiable for understanding cubic moduli given as a product of three linear factors. Let's visualize this transformation together. Imagine a standard cubic graph. It usually looks kind of like a sideways S-curve, right? It crosses the x-axis at three distinct points because of those three linear factors. Evidence-based reasoning means you don't just guess that shape. You prove it. You check the leading coefficient. Is the x times x times x positive or negative? If it's positive, the graph starts bottom left and ends top right. That is your base evidence. Once you have that base curve sketched faintly in pencil, you apply the modulus. Everything below the x-axis gets flipped upwards like it's hitting a perfect mirror, creating these really sharp V-shapes or cusps right at the roots. You have to actively reason your way through this systematically. Let's move to the third section and see how all of this builds into our actual methodology. I'm going to reveal the exact procedural framework to you. This is the step-by-step standardized sequence that you can use for every single cubic modulus question you will ever face. It is essentially your master recipe.
Walk through this 5-step standardized sequence with me. Step 1. Identify key elements. Look at the three linear factors and instantly extract your roots. Step 2. Apply relevant principles. Find your y-intercept by setting x to 0 and determine the overall positive or negative shape of the base cubic. Step 3. Execute analysis. Sketch that base cubic faintly. Step 4. Verify results. Apply the modulus, reflecting the negative sections, and rigorously double-check that no part of your final graph dips below that x-axis. Step 5. Present appropriately. Darken your final curve and label your axes and intercepts. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
All right, let's put this into an interactive workshop right now. This brilliantly illustrates how critical data interpretation skills are within our procedural framework. In an exam, you might be given an algebraic text or perhaps a complex data table of coordinates. You must scan that data quickly. We call this our data scan challenge. I'm putting 60 seconds on the clock right now. Imagine you see y equals the modulus of x plus 1 times x minus 2 times x minus 4. Go! You must instantly extract the core trend, roots at -1, +2, and +4. You must interpret the relationship to find the y-intercept. It's the modulus of 1 times -2 times -4, which is exactly 8. Then, you draw your evidence-based conclusion by sketching the curve, ensuring it touches the x-axis at those roots and bounces back up, forming those distinct, beautiful cusps. Boom! Full marks.
We are now entering our final, and honestly, perhaps our most crucial agenda section, Top Examiner Warnings. This is where we focus heavily on the evaluation phase, the final plating of your dish, and we are bringing you insider insights straight from the people who actually mark your 0606 papers.
Ask yourself this tension-building question right now. Where do most students actually lose their marks? You might think it's because they can't do the complex algebra, right? But a critical analysis of the principal examiner reports reveals something completely different. Earlier, we talked about SAM. In our workshops, we often run a Find the Flaw challenge, where we show a flawed sample paragraph of mathematical reasoning from a student exactly like Sam, and we ask the audience to identify the exact sentence losing marks. It's fascinating because the results perfectly align with the examiner's own reports year over year.
Here is the breakdown of the top 3 mistakes students make. First, confusing cause and effect. Students often try to draw the modulus reflection before they've even accurately established the base cubic curve. You absolutely must establish the cause, the underlying cubic function, before you apply the effect, which is the modulus. Second, forgetting format and presentation. Examiners literally hate a messy, ambiguous sketch. Presentation follows strict conventions. You need proper access headings, clear annotation of your x and y intercepts, and smooth curves that do not look like straight, jagged lines. And crucially, except at the roots where the modulus creates a sharp, distinct cusp, the rest of the curve should be smooth. Drawing a rounded, U-shaped bottom where a sharp V-shaped cusp should be will absolutely lose you marks on the spot.
Third, answers lacking specific context. This means ignoring the domain given in the question entirely or sketching way past the required X values.
Listen to me very, very carefully here, because this is the absolute climax of your entire exam strategy. Examiner alert, show you're working. The method mark strategy is your ultimate safety net. We even do a 30-second speed writing challenge for this. Why? Because even if, under the immense pressure of the ticking clock, your hand slips and your final graph sketch looks a bit wrong, method marks will literally save your grade. Examiners actively reward the process. If you clearly write down x equals ABC to prove you found the roots, and you calculate f of 0 to explicitly show you found the y-intercept, you are banking points. Do not just draw the graph in total silence. Communicate your mathematical cooking process clearly on the page.
Furthermore, evaluating evidence quality is what genuinely separates the B students from the A-star students. How does this apply to sketching graphs? Well, it means identifying limitations, recognizing that a sketch is not a perfectly plotted graph, but understanding it must still proportionally represent the distances between the roots. It means stating assumptions, like understanding that the cubic curve is continuous. And it means providing alternative interpretations. For example, knowing that if a tough question asks for the number of solutions to the modulus of f of x equals k, you can visualize a horizontal line y equals k intersecting your graph and just count the intersection points. Understanding how the quality of your sketch directly affects your ability to draw further conclusions like that is elite-level mathematics.
Let's do a final recap of the ultimate exam strategy sequence for mastering these cubic modulus graphs, essentially our time management matrix. 1. Deconstruct the command words. Are you plotting or sketching? 2. Extract the relevant data, meaning your roots and intercepts. 3. Select the analytical framework, applying our peel structure. 4. Execute with clear notation, showing absolutely all your method marks. 5. Present with correct terminology, clearly labeling your cusps and axes so the plating is perfect. Listen, students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos.
Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at AC Exams IGCE to excel in your Cambridge examinations. Subscribe right now to @Ace the Exams IGCE and click that bell. Don't let another exam pass you by. Master the process and you secure the A-star. It's all about the evidence, the analysis, and the evaluation. Now, I want to hear from you. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. I'll see you in the next explainer.